And if just, I'm gonna be watching from there. If that goes away, just let me know.
Yes. Okay. If this one, if it's not matching the.
Yes, it might move a little slow, but it's also. But if it goes away, I gotta come back.
All right, everybody, let's go ahead and get started. So today's seminar, we have a special works heavily with works assistant. Computer science. Give your attention to Ahmed and Alksas today.
Hello, everyone. So today I am going to talk with you with the role of AI in early diagnosis of lung cancer. So we will go through the challenges and the optimal solutions that AI can provide in this field. So lung cancer is the leading cause of cancer deaths, and it's the second most diagnosed cancer in the US. So we can say that in the US, it's like one out of every 4 cancer deaths are resulting from the lung cancer. There is a clinical hypothesis that says that if the lung cancer had been diagnosed at early stages, this might lead to lowering the mortality rate and trying to find optimal treatment or optimal intervention solutions for this. But the issue with the lung cancer at most of times it shows symptoms at later stages, and at these later stages, the solution or the treatment solution are so limited. So in here we hypothesize that if we are able to find like an approach that can detect lung cancer at early stages, this might lead to decreasing the mortality rate of the cancer. Currently, the gold standard for diagnosing lung cancer is the needle biopsy. But the main issue with the needle biopsy, as it has some high risks of bleeding, it sometimes causes infections. So we are trying to find a non-invasive manner or a non-invasive approach that it can lead to diagnosing lung cancer at early stages. Basically, the needle biopsy is a second. The needle biopsy happens after the imaging, or like basically the computed tomography. It tells us that there is an issue with the lung. So this comes at later stages. In the era of artificial intelligence, or in the literature, there are multiple approaches that have been proposed and published in diagnosing lung cancer using artificial intelligence-based techniques. But most of these approaches, they have some drawbacks or some flaws, like the high false positive and negative rates in the traditional approaches. Also, there is a lack of integration of combining local and global descriptors. So the approaches that are there, it's either using the machine learning classical vision or using the deep learning. Also, there is more limitations in the generalizability and the sensitivity of these approaches. For this, we are proposing 2 solutions or 2 frameworks for the lung cancer diagnosis. The first one is utilizing a modified local ternary pattern to quantify the heterogeneity or the homogeneity within the lung nodules. And the other one, it's a more advanced approach. It integrates multiple features like the homogeneity and the morphology of the lung nodules with advanced vision transforms. we have two data sets in here. One private data set, it's collected over 5 years in University of Louisville, and the other one is a public benchmark data set from LIDC. So let's start with our first approach, which is entitled a novel higher order appearance texture analysis for diagnosing lung cancer based on a modified local ternary pattern. So here is basically the framework of our approach or our technique. The main or the clinical hypothesis in here, as we got after discussion with our medical collaborator, that the malignant lung nodules, they have like some complex patterns and some multiple differences in the texture of the nodule itself. So if we are able to detect this heterogeneity or the inhomogeneity within the lung nodules, we can find a solution, or we can classify between the malignant nodules and the benign ones. So in here, before going with the details, what we are doing in here, we are trying to quantify the inhomogeneity of the lung nodules. We are extracting the nodule itself. We are trying to quantify the inhomogeneity and extract the feature vector. This feature vector is then fed to our classification model, which is a stacking-based architecture. We will go for this shortly. So our inhomogeneity detection approach, it's a little tweak or a little modification for the traditional local binary pattern. The main idea of the traditional local binary pattern is that you can compare each pixel within the nodule to all its surrounding, and based on this comparison, you can quantify the homogeneity or the heterogeneity. In other words, we are trying to see or to quantify how each pixel is compared to its neighbors. The problem with the traditional approaches or the traditional local binary pattern is it's binary. So it doesn't correspond for the level of heterogeneity between the pixel and its surrounding. So let's say if we have a pixel and its surrounding, it has the difference between the pixel and its surrounding. If this difference is like 15, it will be the same if it's 100. So we can say the flexibility of the approach itself or the inhomogeneity itself is not that advanced. So in here, in our modified approach, we are trying to quantify the inhomogeneity in 3 levels. We are trying to capture 3 levels of inhomogeneity based on two thresholds for the difference or 2 cutoff values. So basically, in the local patterns, we have two main vectors or two main approaches. The first one, the first vector is the decision vector. This decision is how the pixel is compared to the other to the neighborhood, to its neighbor pixels. And the other one is the rank vector, is how these neighbors are positioned regarding to our pixel. Okay. So this is a mathematical example. So if we have like the central pixel is like 143, and we have a surrounding one with 111, and we are having our thresholds like 17 and 55. So in here you will find the difference. It's almost 32. So it's between the pair of thresholds. So we will give a decision of 1. If the difference is higher than the second threshold, so we will assign a decision with 2. If it's lower than both of them, we will assign a 0 decision. Here is the mathematical model of our approach or our technique. So after getting we have to conform or to have our transformed or heterogeneity volume. we have the original nodule. We iterate over each voxel or each pixel within the nodule. We compare it to its surrounding, and then we have the final value or quantifying the heterogeneity. So now, after having our transformed volume of interest, or after getting the heterogeneity levels of all the pixels within the nodule, we need to quantify these values to find like a feature vector to be fed later for the learning model. For this, we are simply extracting the histogram of the transformed volume. This feature vector or the histogram, it should describe the texture or the heterogeneity within the nodules. Of course, what is happening in here, if we are having like a high values or high occurrences of high values of heterogeneity, this means that the nodule itself is totally heterogeneous, and mostly this will be a malignant one. If we are having the occurrences, the most occurrences with the lower values of heterogeneity, we are talking about a benign one. So after extracting the feature vector for each pulmonary nodule or for each nodule, we pass the feature vector, these feature vectors to a two-stage stacking-based classification model. In the stacking-based classification model, we have two layers of machine learning classifier. The first layer, or sometimes it's called the base layers, it has some independent machine learning classifier. Each classifier of these are dealing with the feature vector and trying to get probability or prediction for itself on these inputs. Then we have the second layer, which is sometimes called meta layer. This meta layer tries to fuse all the predictions or all the probabilities that we had from the first stage towards getting the final diagnosis. So in here, in this model, we have some parameters that needs to be tuned. The first thing is, and it's basically the most important thing to tune in here, is the thresholds that we can use to find the heterogeneity. How would we get the decision for these? For this, we are trying to we applied empirical search or grid search to find the optimal pair of thresholds. And as you can see in here, however these cutoff values are changing, it has a direct effect on the final accuracy on the system. We found that the optimal pair of thresholds are 17 and 55. So if the difference is lower than 17, we have a zero decision or a zero in homogeneity. If we are having the difference between 17 and 55, we are talking about a one decision or a medium heterogeneity. If we are having the difference over 55, we are talking about the highest level of heterogeneity. The other thing that we need to hyper tune in here is the learning model itself. So the first symbol or the direct approach that we can apply in here is that we have each classifier, even in the first layer or in the second layer, we try to tune each one of them, and then fuse all of these. We are trying to find the optimal classifier, the optimal independent classifier, and then fuse them and find the final output or the final performance. But the issue in here that happens that even if we try to find the optimal, let's get back in here 1 second. So let's say at the first layer, we can find as an independent manner, we find the optimal random forest at the first layer on its own, and the optimal decision tree, and etc. Combining these optimal ones doesn't lead to the overall optimal performance. so that we need to do like an optimization or a hyperparameters tuning for the whole model as one unit. For this, we applied genetic algorithm. Genetic algorithm made us to or enabled us to find the optimal hyperparameters of tuning the whole model as a whole unit. It's much more faster than the grid search, and it enabled us to find these optimal hyperparameters. So we applied the genetic algorithm with 20 generation and with a population size of 24 and a mutation rate of 0.9 and a crossover rate of 0.1. Here is the initial results that we had for this model. We tried three validation approaches: leave one subject out, 10-fold and 4-fold. We had some performance metrics like the accuracy, sensitivity, and specificity, and area under rock curve. As you can see in here, we have good results in most of the performance metrics. Finally, as a conclusion for this model, you can see in here in this graph, you can see a visual representation of what is happening in here. So at the first row in here, these are the original slices with the original Ahmed field unit-based CT scans. If you look over here over the malignant and the benign and the original ones, you will find there is no clear or sharp differences between the benign and the malignant. As if you can see in here, in the benign, you will find some heterogeneous solutions. The same with the malignant. So by our naked eye, trying to only depend on the texture or the heterogeneity from the original one, it's much more hard. In here, in the second row, there are the transformed slides. Here using the traditional local binary method, and here using our. And as you can see, the major difference between the benign and the malignant of our approach, even the divergence, as you can see in this curve, there is a large divergence distinction between the malignant curve and the. And this is our first approach. Our second approach or our second framework is a novel AI-based diagnostic system for lung cancer diagnosis. It integrates multiple local descriptors with the advanced vision transformers. Here is the framework. What we are doing in here is that we are trying to do like a synergy between the traditional classical vision approaches with the transformative power of deep learning. We are trying to get best of both worlds in here. So the classical vision approaches, it has much more interpretability and has much more specificity, and you can go ahead and force the clinical hypothesis directly within the extracted features. And the deep learning approaches, or especially the transformer models, it has highly grained insights or deep insights that we can extract from our nodules. So as you can see in here, the approach starts with extracting the original volume of interest for each pulmonary nodule. We are dealing with 3D nodules in here. So the segmentation or the delineation of the nodules is operated by radiologists using a 3D slicer. After extracting the original volume of interest with the original values of Hounsfield field unit, we are doing something which is called isotopic resampling for these nodules. By isotropic resampling, what we mean in here is that the after taking a radiology image or something like this, we are trying to get like a unified resampling for each pixel or a unified distance. So mostly the pixel representation or the pixel differences, which are dx, dy, and dz, mostly they are different. So we are trying to find a unified representation in here. We try to get the voxel with dx equal dy equal dz. Why is this important? As it makes our approach scale invariant and the translation invariant, and it also enable us to use data from multiple centers for better generalizability. Then after extracting the original volume of interest, we have two classical vision approaches or two classical vision transformation in here. The first one is similar in its essence to the last one we talked on, but with simple modifications. And so we still trying to capture the heterogeneity within the nodules. And the other one, we try to capture the overall morphology or the complexity of the pulmonary nodules. Then now after having three transformed representation of each nodule, we utilize or we apply a transformer model classification approach. So the first transformation approach, or the first feature that we are trying to capture in here is the heterogeneity. So we still using the modified local ternary pattern with some modifications to get over the challenges within the old one. The main limitation with the modified local ternary patterns that we talked at our first approach, that it has some high weight for the position of the neighbors related to each central voxel. For this, the model is not, the first model is not rotation invariant, and so what we are doing in here is that instead of having like a cube or a block around each pixel and trying to find the differences in here, we apply multiple spherical regions with increasing radii around each pixel. So we start with the pixel itself or the voxel itself. We find the first sphere around it, and we compare the pixel to the average of all the pixels that are included within this sphere. And based on the two thresholds, we find a decision. After getting done with the first sphere, we go for the next one with an increasing radii. Let's say with a radius 2, find the average of all the pixels included in this sphere and compare it, and so on until finding our final sphere. After this, so we have in here, this is our original one, and after iterating over the pixels in here, we have our final or our transformed output volume in here. Each pixel has a new value which quantifies the overall heterogeneity around it. So we still having a dual threshold. Here's the mathematical model for it. So again, the key benefit in here, or the main modification in here over the modified local ternary patterns that we talked in our first approach, is achieving the rotation invariance in here, as we have nothing to do with how the pixels is positioned around each voxels, or we don't have like if we can say we don't have the rank vector, if you remember from the first approach. So this makes our model rotation invariant. The second transformation that we are doing in here is using local spherical harmonics with some modification to the traditional spherical harmonics approach. Let me talk to you a little bit about the traditional spherical harmonics. The traditional spherical harmonics approach, the main idea of it is trying to capture the overall complexity or the morphological changes that happens around in the surface or the outer surface of the pulmonary nodule. How this is done, we start with like the unity sphere, or the unity sphere is mostly the larger sphere that can fit inside the pulmonary nodule itself. Then we are trying to allocate more spheres. We are trying to allocate more spheres over this unity sphere to trying, in our approach, we are trying to find we are adding these spheres one by one. We are adding these spheres one by one till reaching the outer, till combining or conforming the overall shape of the nodule itself. Excuse me. And after, excuse me, and after adding each sphere in here, we do smoothing. We are trying to smooth the surface and we are comparing the reconstructed mesh over here with the original volume or the original morphology, and we find the reconstruction error. And we iterate over this till we reach the saturation or the divergence within our model. This is the traditional spherical harmonics, and the reconstruction errors over adding spheres one by one, which is sometimes called the harmonics steps. This reconstruction error gives us a quantification for the overall complexity of the nodule, as if we are having like a simple shape or a simple morphology for a nodule, so it will need a little bit of sphere. But if we are having a more complex nodule, so we will need more spheres to reaching our divergence. So that is with the traditional. The main problem with the traditional approach or the traditional spherical harmonics that it's only depend or it only looks over the outer surface of the nodule. In our modified approach, what we are doing in here, we try to adding to beside having the outer surface or the outer complexity of the nodule, we are trying to get the complexity within the inner areas within the nodules. For this, we are applying fast marching algorithm to extract the inner surfaces within the nodule. But instead of getting these inner surfaces or the tangent isosurfaces using the distance, we also look for the heterogeneity or the homogeneity within these. So we are trying to find multiple tangent isosurfaces that are mostly homogeneous. So we are combining the most homogeneous pixels together to form the first isosurface, then going deep within the nodule, try to find the second layer of homogeneous pixels and reaching our inner area. So after having our tangent isosurfaces, we treat each isosurface like an independent mesh, and we apply the traditional spherical harmonics over it. So now the main problem, if we are talking about the traditional approach or the classical vision approach in here, the classical spherical harmonics approach in here, we can find like we can say that the feature vector in here can be just the reconstruction error. But how can we apply this in here? We have multiple isosurface and each isosurface has a vector of reconstruction error. For this, and since we need a transformed volume, we don't need a feature vector in here. So we are mapping the reconstruction error for each pixels with its corresponding reconstruction. Excuse me. We map each pixel to a new value which corresponds. Excuse me. So we map each pixel to a new value. This value is the reconstruction error of its corresponding isosurface or the isosurface that it belongs to. Okay. So this is a visual representation of our transformed models, our transformed volumes of interest using the first heterogeneity using the modified local ternary pattern, and this one using the reconstruction error mapped volumes. So at the first column, you can find here, you can see this for the heterogeneity. The color code in here is the high heterogeneity and low heterogeneity or homogeneity in here. As you can see in the malignant ones, compared to benign ones, the malignant ones contains much more heterogeneous or high heterogeneity over its surface, which is not the same. Which not is the same in the benign. As you can see in here, there are multiple low homogeneity or high homogeneity within the benign ones. This is for the ternary pattern. And if we look in here for the spherical harmonics or the complexity of the models, looking into the inner isosurfaces in here, you will find the color map in here. It codes or quantifies the complexity. So looking in here in the malignant ones, you will find at the inner areas there are less lower complexity in here when compared to the benign. As you're looking in here in the benign, you find much more lower complexity in the inner areas. So now for each subject, we have three representations for each subject. The first one is the original Hounis field-based unit. The second one is the heterogeneity quantified spherical modified local ternary pattern, and the final one is a morphological representation using spherical harmonics. Then we need to synergize these models or deal with these models with a transformer classification model. So we start with the feature extraction. We are using in here the efficient net as the backbone of our model. So each representation goes over a 3D efficient net to extract the feature vectors in here, the global feature vectors in here. We have like for each representation, we have a feature vector of 512 features. So each subject is represented by 3 feature vectors, each of a length of 512. Then these feature vectors are fed to the transformation or to the transformer approach. The transformer in here it deals with each representation or with each feature vector as embeddings. It tries the transformer in here. It tries to find the spatial interactions between these features. It tries to aggregate. After this, we're using learned positional encoding to find these relationships or interactions between the features. Then the transformer aggregates all of these using an attention layer and aggregates these over a final classification layer toward finding the final diagnosis, either benign or malignant. Again in here in this model, we are having much more hyperparameters that we need to tune. For the spherical modified local ternary pattern, it's like the old one. We need one here to find the optimal thresholds values, as this has a direct effect over the overall performance. In this approach, we find that using the spherical patterns, we find that the optimal threshold are 14 and 75. For the spherical harmonics, the main hyperparameters or the basic hyperparameters that we need to tune in here are the smoothing level or the smoothing iterations that we will try to do, and also the number of the harmonics steps, how many spheres we will add or we will utilize for each nodule. For the learning model, we need to also fine-tune the parameters, either for the efficient net itself. The efficient net itself, we try to find the optimal hyperparameters of it, and the transformer model also needs to find the optimal number of layers that are used, the number of attentions has, and so here are the optimal hyperparameters. If you have a look on these. For this approach or for this framework, we utilized two experiments. We tried with two experiments on two data sets. We tried with our private data set. We did like a train test split with 80-20%, and to find the advantage or the added value of the fusion, we started with each representation on its own. So we started with the Howard's field based for only the original transformation. Then the modified local ternary pattern and the spherical harmonics. Then we experimented with the overall fusion. As you can see in here, the fusion led to almost perfect performance matrix, and it's much more better. It's much more better than dealing with each one independently. So after going on our private data set, we created like a learned model. We get our learned model, and we are trying to assess the generalizability. What will happen if we apply this learned model over unseen data? So we went with the LIDC benchmark dataset for external validation. So in here in this experiment, these benchmark data are totally unseen within the private dataset, and with a learned model, and they are totally different from it. And as you can see in here, with the blind test in here, we are having almost the same performance metrics, especially within the fusion. So getting lower from 99.3 to 99.1 in the accuracy and other. So this shows us that our model is much more robust, and it can be generalized over unseen dataset. Wasn't, to be honest with you, wasn't the case with the first approach. As dealing with the first approach, which was using only the heterogeneity. No, we need to the generalizability of it didn't lead to high performance. Finally, for the future in here, we are trying to we plan to optimize or incorporate much more markers in here, or much more representation. So we already started with adding some clinical markers to our model. So instead of dealing only with the transformed classical vision approaches, we are adding some clinical markers. The main markers that we are dealing with right now is the breath analysis itself. So we are adding some these markers, and also we starting to explore the pathological markers or the pathological images of these. Then we trying, and we already started with this. We are developing a user-friendly approach. As basically what we are doing in here, we are trying to find a recommendation system. This is not a standalone diagnosis system. It's a recommendation system that can tell the radiologist or the clinician, this is our recommendation. We can make him see the interpretable representation, and based on it, he can have the final decision. So we started with a graphical user interface of it. Finally, since the generalizability of our model is too high, we are exploring applying it over multiple diseases or other diseases to see how this approach or this model will perform with other diseases. Finally, I want to thank my advisors, Dr. Adel Maghrabi from Computer Science and Dr. Baz. My team members, Dr. Eric Van Bogert, he is at the Department of Radiology at University of Louisville, Dr. Ahmed Suleiman and Dr. Ahmed Shafi'i and Dr. Ali Mahmoud. And finally, all the team members of Bioimaging Lab for their continuous support. Thank you. And if you have any questions, thank you.
From what you learned between the SM and SH, thought that there was the greater heterogeneity on the outside and then like a higher on the inside difference as like in the 9. Could you use that information to define other HU thresholds that could potentially be better than the current one as a more simple application?
So you've got the thresholds in it, and the thresholds in it has a direct effect on the overall performance of the quantification of the heterogeneity. But in the second model, it's the approach itself is less sensitive to these differences. First one, whenever you change the thresholds, it's totally different. Some thresholds lead to accuracies lower than 50%. But in the second one, as we are synergizing more approaches, it still has the essence of the deep learning. So the effect of changing these thresholds are. So is this what you?
I think so.
Far away are you having it in that you're working?
Starting to explore it with the clinicians. Basically, for the one answer, there is a general refusal since I know some of the attention we set this one I need. So we are trying to find some interpretable models for them. So what we are trying to do in here and the first point of contact is Dr. Eric. I won't tell you that I'm having a malignant nodule or a benign one, or what I will tell you for a clinician, and you told me that the clinical hypothesis of you that the malignant nodules have some complex patterns of texture compared to the benign ones, and they are having much more complexity on its surface than the benign ones. So I will show him this representation. Looking over the code, he will decide. So even Dr. Eric, when he saw this representation, he told me that you don't need to proceed was classification. So to me, for the estimating, if we find some blue patches or more blue patches, I will consider this or have like a voice telling me that this is a benign one. If I had like almost all red patches within the ternary pattern, I'm talking about a benign. And in here, to the spherical harmonics, we try to negotiate a little bit of how this conforms to this hypothesis. So in here, we are trying to synergize the overall complexity over the surface within the inner homogeneity or the inner isosurfaces in here, as these tangent isosurfaces are based on the homogeneity. So not based on the distance from the center to.
Is the ultimate goal of this is to use it on segmented lung nodules that have already been identified as like a potential? Because I like you're saying the doctors wanting to really just do a biopsy for testing. Would that, the more effort required to be able to segment it, would that end up offsetting just end up having to do the biopsy in the first place?
No, this is a current approach is right now. Since you are 10 years or something like this, so you need to do like manual segmentation for all the nodules, but currently had some work on using visual, using unit and unit, selecting the nodules itself, and the good news in here is that this is the only thing that all the clinicians agrees on. So all the clinicians they find like if I'm trying to manually segment the nodules itself or trying to delineate the nodules itself, this is high work for them. So if you find a solution that automatically segments the nodules for themselves, so they are happy with using the automatic segment. Especially in the second model, the fine details or having an exact segmentation in here is not a must, as we are dealing mostly the most information we are getting in here from the inside is not only the complex. So if we have like some differences, or we can say some errors within the segmentation itself, it won't affect the. One other thing is that using this, and I already started with this, using the spherical modified Lucatanian pattern, we can use this one over all the slide, not only the hardware, as the nodule itself, especially at later stages. It have multiple changes on the outer tissue or the surrounding tissues.
Which, and that actually, I don't know much about like lung cancer, so is the way it appears on imaging, does it differ for different types of cancers that end up in the lung, or is it only for certain?
Any other questions? الموضوع صعب اكتر من كده. معظم
It's like constantly dying.
Yeah, because I'm pretty sure you emailed them. Yeah.
I'll just let you know that, during the, it's a little late, but I looked at my last report, like grade, the point skills. And I was looking at it, and, I was trying to make sure like this. I didn't notice how much passive language I use. It's so, but I was like, really? And I'm so good, like, this man has a possibility.
It's difficult.
And then, I'm gonna try to do the 3 ASSP, but, I don't know which one are too long. Can I go to like cast seminars, like, or whatever that's like 2, that's seminars, like, you know, the ones that I already done. Anyone that I haven't done.
The full report, that's whenever.
That makes sense. I just want to think, sure. But yeah, this one should be a lot better, for the passive language. I did use 2 sources, and I used EndNotes, the citation, but, I don't know that is what you're really looking for, so I looked again, that you look for more examples in the background. I don't know if I really, or more examples of results in the background. I don't know if I really did that. This last one, the one I did on. Yeah,
Things hard to sit there.
Put references for just plain general of primary preliminary bypasses and most of the techniques you have classifications. Besides that, everything else I just cite also a citation to the seminar itself.
Yes.
But that's really it. That's my only 2 sources. If it was like a general practice or if it was like playing in the background for the actual techniques used, I use this. Just to get more background information.
And that's what we want you to do. And like I said, if I feel like